The horses in this image are all the same color, and I can prove it. In fact, I can mathematically prove that all horses everywhere are the same color. How, you ask? Well, to first understand that, you have to understand what mathematical induction is. Okay, so what's induction? Well, it's a way for you to prove that a statement that depends on a natural number n is true for all the natural numbers. The natural numbers, of course, are just the counting numbers. 1, 2, 3, and so forth. For example, suppose that I wanted to prove that if you add up the first n natural numbers together, you get n times n plus 1 divided by 2. But I thought you wanted to prove that all horses are the same color. I will, just hold your horses, okay? Anyway, well, one strategy that I could use to prove that the first n natural numbers add to n times n plus 1 over 2 is to do two things. First, I could show that it's true for what's called a base case. In this case, we'll show that it's true for n equals 1. Second, you show that if this statement will work for n equals k, then it's also going to work for n equals k plus 1. This is sometimes called the induction step. Well, the two work together as follows. The base case says that it works for n equals 1. But then the induction step says that if it works for n equals 1, then it has to work for n equals 2. Then the induction step says that if it works for n equals 2, then it has to also work for n equals 3. Well, then it says that if it works for n equals 3, then it must work for n equals 4. Well, then it says if it works for... you get the idea. Anyway, the process instantly moves through all the natural numbers and shows that it's true for any natural number that you pick. We can illustrate this another way by using a book and a few copies of myself. Hi! Okay, guys, we're going to play a little game, and there's only one rule to it. When someone to your right hands you a book, all you have to do is pass it to the person on your left. Got it?
Yeah, that sounds pretty easy.
Okay, then, go for it and play the game. Why aren't you guys doing anything? Well, no one gave us a book. Oh, so this rule on its own doesn't do anything in the game unless someone actually hands you a book. Well, let's see what happens when I do that. Thank you. Thank you. Thank you. Thank you. So when you have the rule and someone hands you a book, the book will go through everybody's hands. This is exactly what are you guys still doing here?
I don't know. We're not really sure.
Oh, well, you guys can disappear. I don't need you anymore.
Disappear?
Ah, crap. The rest of you too, please.
What? Who?
Oh, that was weird. Anyway, like I was saying, this example with the books and my other selves is just like induction. To make an induction proof valid, you have to do both the induction step, which is like me giving my other selves the rule that they have to pass the book on whenever they get it, and the base case, which is like me giving the first one of them a book. Now, to see how this works in practice, are we going to talk about the horses yet? Nay, we need to finish off our example first. Hey, I thought we got rid of you. Ah, man, not again. Anyway, let's prove that the sum of the first n integers is n times n plus 1 over 2. First, we prove the base case n equals 1. Here we have that n times n plus 1 over 2 is really 1 times 1 plus 1 over 2, which is just equal to 1 times 2 over 2, which is 1, which indeed is equal to adding together all the natural numbers up to 1. Now for the induction step. We want to prove that if this formula works for n equals k, then it also has to work for n equals k plus 1. So we assume the hypothesis that 1 plus 2 all the way to k is equal to k times k plus 1 over 2, or if we simplify it, k squared plus k over 2. Now let's try to prove that the formula works for n equals k plus 1. That is, we want to show that 1 plus 2 plus all the way to k plus 1 is equal to the quantity k plus 1 times the quantity k plus 2 over 2. See how that's plugging in k plus 1 for n? Well, if we start with that left-hand side, we have that 1 plus 2 plus all the way to k plus 1 is equal to 1 plus 2 all the way to k, quantity, plus k plus 1. Well, that first k elements is equal to k squared plus k over 2. We just did that with the induction hypothesis. So if we write that out, we have k squared plus k over 2 plus the quantity k plus 1. Well, now we can combine that into a single fraction, and sure enough, it simplifies to the quantity k plus 1 times the quantity k plus 2 all over 2, which is exactly what we wanted to show. Since both the induction step and the base case hold, this fact is true for all natural numbers n. Go ahead and try it. Pick any number you want, any natural number, 15, 37, 29, and add up all the natural numbers up to that number and then plug it into the formula, and that's what you'll get as the sum. Okay, so what does this have to do with horses and how they're all the same color? Let's take a look at the image. Don't they look like they're all the same color?
That's a horse of a different color!
No, it isn't, and I can prove it, and I'll do it by induction. Specifically, I'll prove that any set of n horses are all the same color for any natural number n. So no matter how many horses you find, they're all going to be the same color. And we can prove this by induction by showing that it holds for a base case and proving that if it works for n equals k, then it also has to work for n equals k plus 1. Sounds simple, right? Well, the base case is easy. If you take a set of one horse, it's obvious that all the horses in that set are the same color, or color pattern if you want to get technical. So the base case holds, no problem. Now for the induction step. Here we're going to prove the following statement. Assuming that any collection of k horses are all the same color, then this will also imply that any collection of k plus 1 horses are the same color. Well, start with an arbitrary set of k plus 1 horses and take one horse out of the group. What remains is a collection of k horses. Now, by the induction hypothesis, we're assuming that any collection of k horses have to be the same color. So these guys are. Now, put this horse back and take a different horse out. Now, notice the horse we just put back, we might not know what color it is. But now we have a collection of k horses again, which by the induction hypothesis says that they all have to be the same color. So this horse we just put back that we didn't know what color it was has to be the same color as the rest of them. Well, those k minus 1 horses were this color, and so this guy also has to be that color. Now, even if we bring in the other horse from over there to give us a collection of k plus 1 horses, we still know that they're all the same color, and we're done. Because we proved both a base case and an induction step, this should imply that the statement we made is true for all possible natural numbers n, which means that any collection of n horses have to all be the same color. And sure enough, they are. What? You don't seem very convinced. Maybe you're looking at one of these horses compared to the other two and thinking,
That's a horse of a different color!
exactly. But at the same time, you might be struggling to find a problem with the argument that I provided. And if you can't find a problem with it, you might be wondering whether induction is a valid method of proof at all. And after it seemed to work so well. Well, never fear. Induction is a valid method of proof. But there's a significant, though subtle, problem with the argument that I gave for the induction step in trying to prove that all horses were the same color. Can you see it? If you want, you can pause the video here or even go back a little bit and see if you can find what the problem is. Or you could just wait 4 seconds and I'll tell you. Did you figure it out? It turns out that the argument that I gave for the induction step in proving that all horses were the same color actually works for large values of k. But watch what happens if we use a very small value of k. In fact, while we know that the base case is true, let's see if our argument for the induction step can take that 1 horse case and move it to the 2 horse case. Okay, similar to what we did before, let's assume that we have an arbitrary collection of 2 horses. Now remove one of those horses. This leaves 1 horse behind, which by hypothesis and common sense has to be all the same color. Now put the horse back and remove the other horse. Well, again, there's only 1 horse left, so by hypothesis, it has to be the same color. But now there's no collection of k minus 1 horses that forces the color on this horse to be the same as the other one we removed. So it could be a different color. So if we bring that other horse back, there's no way that we can logically conclude that this collection of 2 horses have to be the same color.
He's the horse of a different color you've had tell about.
Quite. Thus, the argument we used above is invalid for the first non-base case. It works for all the other ones, but that doesn't matter because it can't get off the ground. This would be like the first guy in that line of other me's not following the rule of passing the book on. Just because the other ones follow the rule, they're still never going to get a book. So all those other cases are sort of in a state where they're obeying the rule that they'll pass the book on if they ever get one, but they never get a book, and so it doesn't matter. Thus, the fact that the induction step works for k strictly bigger than 2 is entirely moot, and our proof that all horses are the same color is completely invalid, which should come as no surprise since there's clearly 3 different color horses here.
A horse of a very different color.
Yeah, so I guess I lied, and the thumbnail is just mathematically echoing clickbait. But if you got this far, that means you enjoyed it, so it kind of worked out, didn't it? Anyway, I hope that this video gave you a decent introduction to induction. Say that 5 times when you're drunk. I also hope that it impressed upon you to be very careful with your logical arguments and be sure that it actually covers all the necessary cases. Because if you miss even one, it can totally break an otherwise correct proof and potentially create a proof of a false statement. Some holes in a proof are fixable and others aren't. But don't be discouraged if you happen to find a hole in your argument. Either figure out how to fill it or accept that the proof doesn't work and try something else. It might also be that the original statement is false, so you might try proving that instead. The most effective mathematicians are highly critical of their own proofs and logic and put their arguments through just as much, if not more, scrutiny than they do the arguments of others. And it's very good practice to do so. Well, that's it for today. I hope that you enjoyed this video, and if you did, please hit that like button to let us know. I hope that you also subscribe to Scholar Sauce and check out all the amazing content we already have and be one of the first to see what's coming next. In the meantime, click here to see why PEMDAS is a lie, or here to see me debate the godfather of the Tau movement. See you next time on Scholar Sauce. Nay, we need to finish. That sounds more like a sheep. Nay, nay.